Hello, in this video we are going to talk about the different kinds of pressure that apply to fluids, and in particular we will define the dynamic pressure. So to introduce these different kinds of pressure, we should start by writing down the Navier-Stokes equation. And the Navier-Stokes equation in vectorial form writes rho du by dt plus u dot grad u equals minus the gradient of the total pressure P plus rho g, the force due to the weight of fluid, plus nu times the Laplacian of the velocity. Okay? So to introduce the first type of pressure, the hydrostatic pressure, I'm going to consider that there is no flow. So in the absence of flow, the Navier-Stokes equation reduces to the gradient of pressure equal rho g. Okay, and because this is in absence of flow, this is a static problem. I'm going to call this pH for hydrostatic pressure. Okay, and so from this equation we can write down the expression of the hydrostatic pressure, pH equals rho g dot x, where x is the vector position. Okay, so based on this hydrostatic pressure, we can write down a change of variable for our pressure. So change of variable, and write down particularly that capital P, the total pressure that we had in the beginning, can be equal to pH, the hydrostatic that we just wrote, plus another pressure. Okay, so the idea is that this is the total pressure. This is the hydrostatic pressure. And this one here is going to be called the dynamic pressure. Dynamic because it is due to forces acting on the fluid and is not due to any static effects which are included in pH. Okay? And so we can effectively plug that into the Navier-Stokes equation. So if we write down the Navier-Stokes equation, provided this change of variable, what we get is rho du over dt plus u dot grad u equals minus grad of pH, and pH is rho g dot x, minus grad lowercase p, that's our dynamic pressure, plus rho g plus nu Laplacian of u. Okay, and these two terms here simplify, and we are left with the Navier-Stokes equation in its simpler form, which is rho du by dt plus u dot grad u equals, these two terms simplify. I've got minus the gradient of the dynamic pressure plus nu times the Laplacian of the velocity. Okay, and this is essentially our Navier-Stokes equation in its reduced form. So in general, you will see the Navier-Stokes equation written in this fashion with a dynamic pressure, essentially considering that the total pressure, that the hydrostatic pressure has been absorbed, and therefore we do not have the presence of this forcing term. If you use this expression, bear in mind that if you write down boundary conditions for the pressure, in general, what we consider is the total pressure, so you need to transform this dynamic pressure into a total pressure to be able to match your pressures coming both from the boundary condition and the equation. Otherwise, if you have to write boundary conditions for the pressure, I would recommend that you start with this equation, which makes it unambiguous. In this video, we've seen how to write down different kinds of pressure for a fluid In particular, we've introduced the dynamic pressure and how to change variable in the Navier-Stokes equation to reduce it down to a simpler version. These two pressure, the dynamic and the total pressure, can be used within the equation, and we need to be careful depending on the types of boundary conditions that we're going to write. This concludes this video on dynamic pressure.